Alright, today I got a nice physics video for you guys. We're going to be looking into bank curves. Wait a second, is there someone here? What the hell, Abdullah? What are you doing?
I'm just checking out your equipment.
What? Get out of here! Leave! Leave! And why aren't you wearing a shirt? Take off my lab coat! What the hell? Oh my god. What was he making? What is this stuff? I might have to run some tests on this. Alright, welcome back to Ubad's lab, and today we're going to be doing a physics problem with a banked curve. Alright, I got the diagram set up right over here for this problem right here. So first we have to understand what a banked curve is. So if we look over here, this diagram can be a little misleading because it can lead you to think that this car is actually traveling down this ramp in this direction. But you need to understand that it's traveling in circular motion and it's just banked inward. So if we look at a bird's eye view, this is a bird's eye view to the car traveling. So here's the car and it's traveling like this, but the ramp that it's the track that it's traveling on is ramped inward. It's tilted inward. So this would be like the left side of the car. This would be the right side of the car. And if we look at this diagram, the car would be traveling towards us. This is important to understand for when we draw our axes because we need to understand in which direction is this car accelerating towards. So in this problem, we want to figure out what's this angle of this bank if this car is traveling at velocity v. So we should start off by drawing a free body diagram. Actually, before we draw a free body diagram, we should draw our axes. So we decide to draw our axes based off where the car is accelerating. Now, the car is accelerating to the center of circular motion. That's one of the fundamentals of circular motion. So it's traveling this way. This is the way of acceleration, right? So if we look over here, acceleration would be that way, right? So we should draw our axes like that. We can just cover that up because that can get confusing for when we do our free body diagram. So let's get a free body diagram with this dot right here. So we're going to ignore friction for this problem to keep it simple, but we're going to go with the force of gravity going straight down. That is mg. And the normal force is always perpendicular to the surface that's on. So the surface is like this, normal force will be perpendicular to that. Fn. Okay, so now we can sum our forces. So let's start by summing our forces in the y direction, the vertical direction. So sum of forces y is equal to may. And we know that this okay, let's start with the sum of forces. So mg, that's going to be negative, so we can do minus mg, it's downward. And then for Fn, so Fn is pointing this way, right? So some of it has some vertical force, but it has some horizontal force. So we need to figure out what component of Fn is in the vertical direction. So we can draw a quick triangle right here and use some trigonometry to figure out how much of this normal force is actually in the vertical direction. So we want this vertical component, right? And we can see that the cosine, let me draw this right here. The cosine and the theta would be this. Cosine theta is equal to the adjacent, which is what we want, the adjacent. I'll put that as x for now, times the the hypotenuse, which would just be the Fn, right? No, it's a cosine adjacent over hypotenuse. So Fn, right? Let's get rid of that. So it's x over Fn. So if we multiply both sides by Fn, we get that x, the vertical component of Fn, is just equal to Fn cosine theta. I'm going to make some space right here. Fn cosine theta minus mg is equal to, now its acceleration in the y direction is just 0 because it's not moving up and down. All it's doing is traveling this way, and it's accelerating inward. It's not moving in the vertical direction. So its acceleration in that direction also has to be 0. So equal to 0. And then we can add mg to both sides to simplify this a bit. So we get Fn cosine theta is equal to mg. Okay. Now let's sum our forces in the radial direction, the x direction, since radial is the same as x, since it's traveling a circular motion that way. So sum of forces in the radial direction is equal to MAR, right? So sum of forces in the radial direction, mg, that's all of the force of mg is going just vertically, none of it's horizontal. So we just have some of this Fn that is going horizontally. So we're looking for this line right here. We'll put this as the y. I probably should have switched this y and x, but it's all the same really. So now if we look over here, we can see that sine of this theta, which is also this theta, basic geometry, this theta is equal to that theta, is equal to opposite over hypotenuse. The opposite of this is the y. Hypotenuse is Fn. Multiply both sides by Fn, we get Fn sine theta is equal to y. Y is the horizontal, the radial component of Fn, so we can throw that into here, and that's the only force we have in the x direction. So Fn sine theta is equal to m times the acceleration in the radial direction. Acceleration in the radial direction is equal to v squared over r. That has nothing to do with this problem specifically. That's just one of the fundamental equations, that the acceleration in the radial direction is equal to v squared over r. And now we have all this information. We have these two equations right here with Fn cosine theta is equal to mg, and we have Fn sine theta is equal to m v squared over r. So there's something we can do with this. We can divide these out. So let's do Fn sine theta is equal to m v squared over r divided by Fn cosine theta is equal to mg. Fn's cancel. Sine over cosine, tan theta. M's cancel, and we get v squared is equal to r times g. The g just goes into that denominator right there. And the question's asking for this angle. This we based it off this angle, but that angle is equal to that angle, the angle of the bank. So we can do inverse tan of this to find that angle, or rather arctan. Arctan of v squared over rg. is equal to theta. There we go. So this arctan v squared over rg is equal to theta. So we solved for the angle of the bank.